Hi, welcome back to our machine learning course. In the previous video, we talked about backpropagation and how to train neural nets. Now, knowing that, we can make informed decisions about which activation functions we want to use, how we want to initialize the weights of the network, and which exact variant of stochastic gradient descent we want to use in our application. And that's what we will be discussing in this video. So now that we understand how neural networks are trained, we can reason about which activation functions we actually want to use. Now, historically, the first activation function that was used a lot was sigmoid, which looks like this. So it's a value between infinity and plus infinity, and it returns a value between 0 and 1. This makes a lot of sense, right? That we want to smooth the outputs into some value between 0 and 1. But we've learned that this doesn't always converge well. And we get much better conversions if we can make the activations, the outputs, around 0, rather than just all positive ones. We can do it with 10H. So 10H is simply, it's like a sigmoid minus 1. It's a bit steeper as well, but most importantly, it's now around 0. So negative values are negative, positive values are positive, but overall they're around 0. The 10H is still used a lot today. It's very popular. It's a bit expensive to compute though. And there's some other problems that we'll come back to in a minute. A simpler approximation of this is ReLU. ReLU is simply the max of the input, max of 0 in the input. So if the input is positive, you just give the input straight away back. So if the input is a 2, you give it 2 back. If it's negative, you give 0 back. So this is still nonlinear, right? It will still allow you to learn nonlinear models. It's definitely less smooth, right? It won't learn smooth boundaries. But the good thing is it's much faster. Note that this is actually not differentiable at 0. Now this is typically not a problem because this input is a float, and the chance that the input float is exactly 0 is very, very small. And even if so, you can just, you can use a subgradient, just like any gradient that stays below this line. But in practice, you could always say that, okay, if it's 0, then just output 0. Now, there's one more variant that's very popular. It's a leaky ReLU, and the difference is that in the negative domain, it does this. So it has a very small 0.01 times z value if the input is negative. Why is this interesting? We can really understand if you look at the effect it has on the gradients. So remember that during gradient descent, the gradients that we compute are the sum of these 3 parts. Right? So it's the remaining gradient in the network times the derivative of the activation function times the derivative of the inputs. Now this term in blue here means that the derivative of the activation function actually defines how large the gradients are in a network. If this derivative happens to be 0, then the gradient is 0. And none of the weights will be updated, and there's no learning happening whatsoever. So we definitely want to avoid that. And also, if this is 0 or very small, it also will drastically reduce the gradients of the previous layers. We call this a vanishing gradient. The signal gets lost, and the early layers cannot update anymore. Now, sigmoid and 10H have a gradient. So this is the original sigmoid. This is a derivative. 10H looks similar. So it's non-zero around 0, but if the value is very large or very small, very negative, then the gradient is almost 0. It's not exactly 0, but it's almost 0, right? Which means that this term becomes almost 0, which means that your gradient will disappear quite fast. Right? So that's why 10H is not ideal if you want a deep network, because the gradients will just very quickly disappear. ReLU does a bit better here. If you look at the gradient of ReLU, it's a constant. Right? It's basically 1 for all positive values. Right? So it's not affected as much by this vanishing gradient problem. So this allows you to build deeper networks. Now, the problem is, of course, in the left side here. If you end up, for some reason, with a very negative input, small changes won't fix that. Right? And it basically the node gets stuck at this zero gradient, which means that the weights are not updated anymore. We call this the dying ReLU. It means that the neuron has basically died. It doesn't change any of the weights anymore. And to fix that, you can use the leaky ReLU. And leaky ReLU has a very small, like 0.01 derivative in this region, which allows it, well, if you end up here, you still have like a small gradient that allows you to recover if needed, right? So you can learn better. So this, yeah. Now in practice, the effect of the leaky ReLU versus the ReLU is a bit disputed. So it doesn't always buy you much. So in many applications, you can still get away by using normal ReLU. But of course, keep in mind that it's an option whenever you happen to run into this dying ReLU problem. If you want to look at the activations, well, the smoothness of the outputs of ReLU and 10H. This is a simple neural network. I think it has 2 layers of 10 nodes each. And we basically, in this case, we use ReLU activation. In this case, we use 10H activation. If you use 2 layers, you can see very clearly that the output, the model that's learned, that's a combination of piecewise linear. The boundary is a piecewise linear function, right, depending on what the inputs are. Right, so given those 2 inputs, x, and given 2 layers, you can have 1, 2, 3, 4, 5, 6, 7, 8, 9, maybe 10 different line segments, and those define the boundary of decision. Well, the boundary between the positive and negative classes. 10H, by being smooth, can learn any combination of smooth functions. Right? So this boundary is a combination of 10 of these 10H curves. So it's much smoother, and well, it can learn much smoother boundaries. However, 10H takes longer to compute. Like with 0.05 seconds for ReLU, almost twice as much for 10H. And the performance is almost the same. Right? So you can reasonably argue that it's not worth it, that you should use ReLU, especially if you want to use deeper network and you don't want vanishing gradients, and ReLU gives you a very good solution. If you look at more layers, because ReLU allows you to learn deeper models, well, then you can actually learn very complex boundaries. Even if they are piecewise linear, you can learn very complex boundaries by just having enough layers. Right? Having more weights means having more flexibility here. So if you go to 4 layers, you can see that the ReLU still perfectly fits the data. And 10H, well, 10H starts to overfit a bit, I think, here, although performance is better. And finally, we have to choose an activation function for the output layer. And this will be specific to your task, right? Because we want the output of the neural network to be in a certain range that we're interested in. Now, if your problem is a binary problem, you can use a sigmoid. The sigmoid will convert any output of the last layer to a value between 0 and 1, 0 meaning the negative class, 1 being the positive class. Right? And then you put it into the loss function and you let backpropagation find the weights so that your predictions of your network will be 1 for the positive classes and 0 for the negative classes. If you have a multi-class problem, you can use something called a softmax. So the softmax is quite simply, it's just a function that converts the output so that the sum of the outputs is 1. Right, so in the simplest form, you can just use the output of one of the output nodes divided by the sum of all the output nodes. Right? So these are all the output nodes, x. This will work, right? This doesn't really reward uh, nodes which are very close. So say they have a node that says zero point 0.9 or a node that says zero point 0.7, right? You want to give a much higher reward to the node that gives a zero point 0.9 than a zero point 0.7. So for that reason, we simply take the exponent of these, and yeah, this will give a big reward to, will kind of push the network to getting really close to the actual true output of each output node. If you would look at this in a graph, say we have here 1, 2, 3, 4, 5, 6, 7, 8, 9 outputs. It will just, and this happens to be these values like -6 and so on. We call this lodges, by the way. So this is whatever the last layer returns. And the softmax scales this so that the sum of all of these, like 0.8 plus 0.19 plus something else, the sum of all these is 1. One problem with softmax is that it tends to be overconfident. So if the output says zero point 0.9, it doesn't always mean that it's 90% sure that this point is positive. It tends to be overconfident in these values. If this is important for your applications and you see that it is indeed overconfident, what you can do is smooth the labels. So what you do, you take the actual label and you have a smoothing variable like 0.01, so that your output is close to 1 if it's 1 and close to 0 otherwise. So say that you have, for instance, 5 classes and one of them is positive, like this one, then you will, the smoothing will do something like 0. I know, 0.5, 0.05, 0.05, 0.05, and 0.98. Sorry for the writing. So the smoothing kind of changes your labels, and that helps overconfident. It's similar to what you see in model calibration. So changing these outputs will calibrate your model better. If your output is regression, then we don't use any activation function. You just directly output the value of the last node, and you let backpropagation learn the weight so that the output is as close as possible to the actual output. So after you've chosen your activation functions, the next thing you should do is to initialize your weights. And there are different ways of doing that. The first thing you could do, but that's definitely not recommended, is to set all your initial weights to 0. The problem with that is that if you now have a gradient and you want to update these weights, well, you know, the rule is something like this, right? Plus theta times the gradient. If all of these weights are 0, it means that after the update, all the weights are the same again. And if all these weights are the same, it's much harder for the neuron to learn how to deal with different inputs. So that's something you don't want, and we call this symmetry breaking. You don't want all these weights to be the same, otherwise you cannot really differentiate between them. What you can do is instead use small random weights. It's definitely a good idea. And so you use small weights between all these weights here. The problem with that is, as you remember, the gradient at some node here is basically a product of the remaining gradients of all the previous nodes times the gradients of these weights here. Which means that if these weights have small values, then the remaining gradient will quickly go down to 0. We call this the vanishing gradient problem. So yeah, that's bad because the signal won't go deep into the network and we won't be able to learn these initial layers. You could, of course, use very small weights, but that has the opposite problem because there will be some paths where you have very large values, and then these weights here, which have high values, will kind of dominate the other ones. And this will lead to zigzagging. So to explain that, imagine you have two weights, Wi and Wj, and Wj is much, much larger than Wi. This means that if you have, for instance, so you have a surface like this, and you are at some point here, and you compute the gradient in different directions, then the update you would have for Wj will be much larger than the other ones. Right? So you have a big update in the direction and a small update in this direction. And of course, you see overshoot, you want to turn around, but the only way to do that is to do something like this because this W is still large. Right? And so what will happen is you will have to zigzag to go down to an optimum. So that's definitely something you want to avoid. And you can do that by choosing random weights which are small. But to avoid vanishing gradients, we want to make sure the variance of the input and the output gradients remains the same. Right? So if you look at all the different gradients in different layers, they should have more or less the same range of values. Right? So they don't go down to zero as you go down to the front of the network. There are some ways to do that. The first of that is Gleurot or Xavier initialization. What it does, well, it looks at a node and the number of connections coming in, we call that the fan in, and the number of connections going out, or the fan out. These are important values because they, well, first of all, they affect how the gradients are computed. If you have a large fan in, then the gradient will quickly, will more easily vanish, while it will decrease faster. If you have a large fan in, fan out, right, the gradients that come in from during backpropagation, they're, well, first, that's different problems. So first of all, they can't sum up to very large values, or they can also update. They all make a correction, right? And some of these corrections may overshoot the correction that you actually need. Right? So for that reason, we want to solve that by making sure that at least the initial weights here are not too large. And so you do that by sampling randomly from a value close to zero, using a normal distribution, right? So it's a normal distribution around zero with a standard deviation, which is the square root of 2 over fan in plus fan out, right? So nodes which have a lot of connections should have a very narrow Gaussian here to sample from. Nodes which have very few connections can sample from a wider range, so they can have larger values. Right? So if you have a node with many connections, these initialized weights should be much smaller. If they have few connections, they can be larger. The Gleurot Xavier initialization were calculated for 10H. If you use ReLU instead, there is an equivalent called He initialization. It's almost the same, but here you only look at the fan-in. And it has to do with the fact that ReLU, of course, is one-sided, so it will have a zero gradient here, so the fan-out becomes less important. Yeah, so it's the same thing, only the computation of the standard deviation here is a bit different. And also larger, right? So ReLU allows larger initialized values than 10H. And finally, if you have a very deep network, even this can cause vanishing gradients. And so to Well, to reduce this, instead of sampling very near zero, we want to allow slightly larger values for the weights, right? Because otherwise, if the weights are too small, the gradient may vanish too fast. So we want instead sample still around zero, but from minus sigma to plus sigma, uniformly. Let's see, sample uniformly rather than in this case where you sample close to zero. And this will again, well, diminish the chance that you will have a vanishing gradient. Now, sometimes you don't have to start from scratch. Sometimes you have other tasks that you've done before, and you have learned good weights on these previous tasks. So why not reuse them when you solve similar tasks? So that's the idea behind transfer learning. So you have a task one, which ideally has been trained on lots and lots and lots of data. It has very good high performance. It's a very good learned weights and very stable. Now we have a second task two, which, well, it's untrained yet. Maybe you have less data than with task one, but you still want to learn this network. What you can do now is, instead of having random initialized values, you can copy part of the network, including the learned weights, to the new network. And this will give you an initialization that's, well, probably much better than just starting from scratch. It will give you a head start. You will need less data. You will converge faster to a good solution. And then the second part here, make sure that you train towards the actual task that you're interested in here. Next to like just initializing and then fine-tuning to a new task, you could also opt to entirely freeze some of the layers, to do not touch them at all. And there's some research about that this definitely helps you sometimes. So to not touch these weights, to not destroy this information, but to kind of freeze these nodes and just let the rest of the network learn a new task based on these representations. This is basically representation learning. Right? If you freeze it, this is basically just representation learning. If you unfreeze it, it's called fine-tuning. And you fine-tune the previously learned weights to a new task. Now, the tricky thing is, of course, which prior task can you transfer from? If the prior task is very, very similar, then this is quite robust, and there have been lots of very cool examples where the weights learned on ImageNet can be transferred to lots of new applications with very good performance. But likewise, on other applications, it didn't work at all. So it really has to be similar in all important ways. And it's not easy to measure such similarity. There are some ways, but not many. And so it's not a panacea for everything. It's still a hard problem. Meta-learning takes kind of a different idea. And here we say, instead of transferring from one task to another, say you have lots and lots and lots of tasks, maybe tens or hundreds of tasks. You learn initialized weights on all of these, and then you learn a combined representation, weights that you can then transfer to the new task. This tends to be more robust, but it's also trickier, and you need a history of prior tasks which you can transfer from.